Good morning and welcome to Saying It's online series. In this session we are going to discuss Euler Cauchy equation of higher order. Today's agenda: general form of higher order Euler Cauchy equation, transformations to reduce higher order Euler Cauchy equation into an ordinary differential equation, and some examples. The general form of a higher order Euler Cauchy equation is x raised to n into nth derivative of y plus an minus 1 x raised to n minus 1 into n minus first derivative of y plus an minus 2 into x raised to n minus 2 n minus second derivative of y plus etc. a1 x raised to 1 first derivative of y plus a0 into y is equal to r of x. It is important to note that in the standard form of Euler Cauchy equation of higher order, the coefficient of leading term should be 1. Here the leading term is x raised to n y raised to nth derivative of y. Here the coefficient is 1. Otherwise, if in a problem it is not like that, we should divide this entire equation by the leading coefficient to make it 1. The solution method is an extension of that in second order. In the previous class we know how to put substitution and how to reduce the second order Euler Cauchy equation into an ordinary differential equation. Here we use the same idea. We put x equal to e raised to t and therefore t is equal to n of x, and we take derivative of this y with respect to t as d, and in the previous session we know x into dy by dx is d into y, and similarly x square into d square y by dx square is equal to d into d minus 1 y. So x raised to 2, there are two factors here, d minus 0 into d minus 1. When there is power 2, here d minus 1. We imitate the same fashion. We got x cube into d cube y by dx cube is equal to d minus 0 into d minus 1 into d minus 2, or d into d minus 1 to d minus 2y. In this way we can find x raised to 4 into d raised to 4y by dx raised to 4 as d into d minus 1 into d minus 2 into d minus 3y. So all the x terms will be disappeared from this equation. Now it is reduced into an ordinary differential equation. And when we use these transformations, the Euler Cauchy equation will be reduced into our familiar ordinary differential equations with the constant coefficients, and the remaining procedures are same. As a tip, in short, the auxiliary equation will be obtained by replacing x cube into y triple dash by m into m minus 1 into m minus 3. See, here we have x cube, so up to m minus 1, n minus 2 factor, m into m minus 1 into m minus 2. Similarly, x square into y double dash can be replaced by, here power is 2, so up to m minus 1 time, m into m minus 1. X into y dash is replaced by m, and y is replaced by 1. In the given Euler Cauchy equation we will get auxiliary equation, and the remaining procedure are same as in the higher order ODE, because when we put all these transformations, our Euler Cauchy higher order differential equation reduces to an ordinary differential equation of higher order. As an example, we consider this one. Solve x cube y triple dash minus 3x square into y double dash plus 6 into xy dash minus 6y equal to x raised to 4 into logarithm of x. Clearly it is a non-homogeneous ODE, non-homogeneous differential equation, and here along with differentials of y there are x terms, and one more thing, the order of differential and the power of x in each term are same, and therefore it is a Euler Cauchy equation. Now we have to find out the homogeneous equation in first stage, particular solution in second stage. So first of all we write auxiliary equation. The auxiliary equation is obtained by replacing x cube y triple dash by m into m minus 1 to m minus 2, that is m into m minus 1 to m minus 2. This minus 3, we take minus 3 to here. Then x square into y double dash is replaced by m into m minus 1, x square. So 2 minus 1 is actually, that is 1, that is a factor in factor part, m minus 1, plus this xy dash is replaced by m, so 6 into m minus this 6 equal to 0. When we simplify this, we got m cube minus 6m square plus 11m minus 6 equal to 0. So cubic equation, we can factorize it, or using a calculator we can find the roots. Here the roots are m1 is equal to 1, m2 is equal to 2, m3 is equal to 3. So using the first rule, yh is equal to c1x raised to m1 plus c2x raised to m2 plus c3x raised to m3. Here m1 is 1, I put 1 here. Here m2 is equal to 2 and m3 is equal to 3. So homogeneous solution is c1 x raised to 1 plus c2 x square plus c3 x cube. Next stage, we are going to find out the particular solution. But look into the right side. The right side of this differential equation contains more than one term in product, x raised to 4 into ln of x. And moreover, ln of x is not a familiar function for us. And so it is better to use variation of parameter or the Wronskian method to find a particular solution. Here we are going to use Wronskian method. So in the Wronskian method, we have to take y1, y2, y3 from the solution. y1 is the term associated with the t1, that is x raised to 1 or x. y2 is the term associated with c2 in the homogeneous solution, and that is x square. And y3 is the term associated with the c3, that is x cube. So y1 equal to x, y2 equal to x square, y3 is equal to x cube. Now we simply recollect the formula to calculate Wronskian. For a third order ODE, the Wronskian should be a 3 by 3 determinant. First row are the solutions, second row are derivative of the solutions, third row are second derivative of the solutions. So I write the formula for Wronskian. Then I substitute the values. y1 is x, y2 is x square, y3 is x cube. Second row is derivative of the preceding row. So that is first row. Derivative of x is equal to 1, derivative of x square equal to 2x, derivative of x cube equal to 3x square. Now the third row is derivative of second row. So derivative of 1 is 0, derivative of 2x is equal to 2 into 1, that is 2. Derivative of 3x square is equal to 3 into 2x, that is 6x. Now we expand the determinant about the first row, first column, because the last term is 0. When I simplify this expression, 2x into 6x, 12x square, minus 3 into 2, 6 x square, minus x square into 6x, 6x cube, 2 into x cube, minus 2x cube. When we simplify this, 6x cube minus 4x cube, that is 2x cube. The next step is finding w1. We know w1 is a determinant obtained from w by replacing the first column. Actually this is w1, the first column, by 0, 0, 1. Now we expand this determinant about the first column, because all other entries in the first column are 0 except the last one. When I expand this, I got x square into x square, x cube, 2x, 3x square. So x square into 3x square minus 2x into x cube, that is 3x raised to 4 minus 2x raised to 4. So we got x raised to 4. We are familiar with this evaluation of determinants in the previous session. Now we are going to find w2. As usual, w2 is obtained from w by replacing the second column by 0, 0, 1. We substitute y1, y3, y1 dash, y3 dash, y1 double dash, y3 double dash in w2, and we expand the determinant about the second column. And so we got minus 1 into, this minus 1 is actually the cofactor corresponding to this element. The position value, row is 3 and column is 2. So position sum minus 1 raised to 5, that is a minus 1 value. Minus 1 into 1, that is minus 1. Then we eliminate this column and the row containing 1. So x cube, 1, 3x square. When we expand this, we got minus 2x cube. Next we are going to find out w3 by replacing the third column of w by 0, 0, 1. As usual, substitute y1, y2, y1 dash, y2 dash, y1 double dash, y2 double dash. y1 is x, y2 is x square, and this element is 0. So derivative of the first row will be in second row. Derivative of x is 1, derivative of x square is 2x, and derivative of 1 is 0, derivative of 2x is 2. Now we are going to evaluate this determinant about the last column. As usual, we get the subdeterminant x square 1 2x only. So x into 2x equal to 2x square minus x square, that is x square. Once you get this w, w1, w2 and w3, we can directly calculate yp using our Wronskian method. So before calculating the particular solution, we have to convert the given equation into standard form. That means the leading coefficient of leading term should be 1. That is very important. So divide the entire equation by the leading term x cube, coefficient x cube, that is the coefficient of y triple dash. When we divide by x cube, we got 1 here, and here actually we have x square y double dash. When we divide x square y double dash by x cube, there is an x in denominator, like that. And the right hand side, x raised to 4 ln of x by x cube. When we divide x raised to 4 by x cube, we got x in the numerator, that is x ln of x. That is a new r of x in standard form. So that is an important point we have to keep in mind, because whenever we apply the Wronskian method to find particular solution of a Euler Cauchy equation, the coefficient of leading term should be 1. So we divide the entire equation by the coefficient of leading term. Here it is x cube. Now we write the formula for yp. Before that, I write down y1, y2, y3, w, w1, w2, r of x and w3 here, because we can easily substitute the values in this equation. So here y1 is equal to x integral of then w1 by w. So w1 is here x raised to 4. So x raised to 4 by Wronskian. Our Wronskian is 2x cube. So x raised to 4 by 2x cube. R of x is x raised to 4 ln of x by x cube, or xn into ln of x. We substitute xn into ln of x. We make the substitution in all other terms. We have 3 terms. y2 is x square into integral w2. w2 is minus 2x cube by 2x cube x ln of x dx, plus third solution, that is y3, x square into integral y3. Here we have y3, w3 is equal to x square. So x square by Wronskian 2x cube. R of x is ln x into ln of x. And we cut similar terms and simplify like this: x by 2. I take this 1 by 2 outside. X by 2 into integral x square ln of x dx minus 2 and 2 get cancelled. We got a minus. I put minus here. So x square into integral. Here we have an x into ln of x dx plus x square by 2 into integral ln of x dx. The next step is just evaluate these 3 integral. First of all, we have to evaluate this integral ln of x, then integral x into ln of x, then integral x square into ln of x. Here we are going to use integration by parts to calculate integral ln of x. So integral ln of x dx can be written as integral ln of x dot 1 dx. So integration by parts. First term is ln of x, second term is 1. This is our integration by parts rule. Integral of uv is equal to u into integral of the second function v minus integral of derivative of the first function u, that is u dash, into integral of the second function v. So here first function is ln of x. Using this rule, ln of x into integral 1. Integral of 1 dx is simply integral dx, that is x, minus integral of u dash. U dash means derivative of the first function. Here first function is ln of x. So derivative of ln of x is 1 by x into integral of the second. Integral of 1 is x. So integral 1 by x dx. This x and x get cancelled. So we got integral 1 dx. So integral dx is x. So integral ln of x dx can be written as x ln of x minus x. Now we are going to find the second integral, that is integral x ln of x dx. Here I take ln of x into x dx, integral ln of x into x dx. I use the same integration by parts. I got the equation x square by 2 into ln of x minus 1 by 2 corresponding to this integral. Similarly, we apply the integration by parts for the third term, integral x square into ln of x dx. We got almost similar, but there is a pattern that we can observe this in integral. in the place of x square by 2 I got x cube by 3 into ln of x minus 1 by 3. So x into ln of x minus x square by 2 into ln of x minus half, and x cube by 3 into ln of x minus 1 by 3. Now we will use all these sub integrals into our yp equation. Yp is equal to x by 2 into x square ln of x dx minus x square into integral x ln of x dx plus x cube by 2 into integral ln of x dx. We evaluate all these integrals separately, substitute it, and simplify. We got x raised to 4 by x into ln of x minus 11 by 6. So we have now yp. So general solution yg is equal to homogeneous solution plus particular integral. Homogeneous solution here c1x plus c2x square plus c3x cube plus the particular integral is x raised to 4 by 6 into ln of x minus 11 by 6. Ln of x minus 11 by 6. So it is important to keep in mind that when we are using Wronskian, the total equation should be in the standard form. Otherwise, it will create an error in the particular solution. So important takeaways: higher order Euler Cauchy equations are actually extensions of second order Euler Cauchy equations. Solution of an Euler Cauchy equation is a linear combination of power terms of x, but in the case of ordinary differential equation, it is a linear combination of exponential terms. We can use either method of variation of parameter or Wronskian method, they are same. Or sometimes there is only a single function right hand side, we can use method of undetermined coefficients also. So the Euler Cauchy equation is a special type of equation. We can reduce it into ordinary differential equation. It may be in second order or higher order. Then we can use the same method for finding homogeneous solution and also for particular solution. So this is all about the solution of ordinary differential equation in the K2 syllabus, in the view of K2 syllabus. Okay, thank you.